Welcome back to the AdBlue Production Unit Series, episode number 4. In this part, I'll walk you through the next stage of the design process in AutoCAD Plant 3D. We'll continue building the system step by step, explaining the logic behind every decision, from equipment placement to piping layout and operational flow. You'll see how each element connects into a functional, efficient unit, and how small design choices impact real-life maintenance, safety, and workflow inside the factory. Let's jump into the model and continue the build. Now that the wall segment is in place, I'm drawing the maintenance walkway. This path helps me visualize where operators will actually walk during maintenance, how they reach pumps, valves, filters, and all service points. By sketching the walkway early, I can check clearances, make sure nothing blocks the access, and ensure the layout is realistic for everyday operation. In industrial layouts, maintenance walkways require certain minimum widths to ensure safe and comfortable movement for personnel. 600 millimeters is considered the absolute minimum clearance that still allows a person to pass and perform basic tasks. It's typically accepted only in tight technical areas where space is limited. 800 millimeters is a recommended standard for regular maintenance access. This width allows an operator to move more naturally, carry tools, bend, and work without restriction. 1000 millimeters is the preferred optimal width for comfortable, safe, and long-term ergonomic maintenance access. It ensures enough room for two-way passing, opening panels or valves, and working with equipment without feeling cramped. Now I'm just adding a hatch pattern, and with that we have our maintenance path clearly visualized. Now I'm working on the top nozzles of the AdBlue storage tanks. These vessels are atmospheric, which means they're not pressurized, so each tank needs a vent pipe at the top. The vent pipe lets air escape when the tank is being filled and allows air back in when product is being pumped out. Without proper venting, the tank could deform or the pumping process wouldn't work correctly. I'm also adding one more nozzle for the level indicator so we can monitor the product level inside the tank accurately during operation. I'm adding the vent pipe with a small bend at the end. The bend protects the opening from rain and debris while still letting the tank breathe during filling and emptying. Now it's time to add the level sensor. In our case, this is a level transmitter, not just a simple indicator. A level transmitter continuously measures the liquid level inside the tank and sends an electronic signal to the operator's control system or monitor. This allows the operator to see the exact tank level in real time, get alarms if the tank is overfilling or running empty, and automate pumping or filling sequences. Level transmitters are much more reliable than visual gauges because they work even when the tank is closed, insulated, or not accessible. Now we can finish our reactor. I'll add a few more nozzles and slightly reduce the vessel size to match the real AdBlue production requirements. For AdBlue, you always need proper mixing. So instead of designing the mixer from scratch, I'll simply import a ready-to-use unit from GrabCAD. GrabCAD is extremely useful for engineering projects. You just register, and you get access to millions of free 3D models. Select the correct file format, download it, and drop it into your Plant 3D project. This saves a lot of time and keeps the model realistic. Here I'm choosing a nice-looking agitator model. The mixer sits inside the reactor, while the motor is mounted on top, aligned with the central nozzle. This top entry configuration is the most common solution for AdBlue reactors. It ensures good circulation, easy maintenance, and a clean mechanical layout. I just place the agitator through the top valve connection, adjust its height, and make sure the shaft is centered inside the vessel. It doesn't have to be perfect at this stage. The goal is to visualize how the mixing system will actually look in the final unit. The reactor also needs a level column. A level column is an external vertical pipe or small vessel that is connected to the main reactor through two nozzles, one at the bottom and one at the top. Because both vessels are hydraulically connected, the liquid level inside the column always matches the level inside the reactor. The reactor also needs a refractometer. A refractometer is an inline instrument that measures the concentration of a liquid by analyzing how much it bends or refracts light. In AdBlue production, this is very important because the final product must reach a precise urea concentration, typically 32.5%. By installing a refractometer on the outlet line or on the recirculation loop, we can continuously monitor the concentration in real time. This lets the operator adjust water or urea dosing immediately without taking manual samples. It's a simple device from the outside, but extremely useful for process control. It ensures consistent product quality and saves a lot of lab work. Now I'm adding a simple nozzle for carbamide urea powder. In real AdBlue production, the dry urea is usually transported to the reactor by a screw conveyor. The conveyor feeds the powder directly into the top of the vessel through this dedicated charging nozzle. The job of the nozzle is straightforward. It provides a sealed, controlled entry point for the powder so it doesn't spill, create dust, or contaminate the area. Once the powder enters the reactor, the agitator immediately starts dissolving it into demineralized water, helping us reach the correct concentration. Now I adjust the height of our demineralized water tank so it fits the layout. I add a simple level transmitter on top to monitor water volume, and a vent nozzle because the tank is atmospheric. It needs to breathe when filling or emptying. I'm also adding a heating coil nozzle for the tank. This connection is used to bring in hot water or steam to an internal coil that keeps the demineralized water at the right temperature. It prevents cold water from slowing down the dissolving process and ensures stable production conditions. I also add a temperature transmitter. It works together with the heating coil. When the transmitter detects that the water temperature drops below the set point, it sends a signal to turn the coil on. Once the temperature reaches the target value, the coil switches off. This keeps the water temperature stable automatically. This automatic valve opens when the level transmitter indicates a low water level in the tank. As soon as the level drops below the set point, the transmitter sends a signal and the valve opens to refill the tank. When the level rises back to normal, the valve closes again. This keeps the tank filled without operator intervention. Just making a few small adjustments to the valves here, adding the hand wheels to finish them off. Now it's time to add the pressure gauges on the lines so we can see what's happening in the system during operation. On the pump's discharge line, we install a pressure gauge to monitor the pressure the pump is creating. It helps us check if the pump is operating normally, detect blockages, and verify that the downstream system is not overloaded. Now I'm adding a Flowmeter on the water line. This device shows exactly how much water we are pumping into the reactor, so we can control dosing and keep the process stable. Now I'm adding an automatic valve. Once the Flowmeter counts the required amount of water, this valve will close automatically and stop the flow. And eventually we select the proper Flowmeter for this application, making sure it matches the line size, flow range, and accuracy we need. Flowmeters always need straight pipe distances before and after the device. This stabilizes the flow profile and ensures accurate measurement. Usually we keep a few pipe diameters of straight run upstream and a shorter section downstream, depending on the Flowmeter type. That's it for today's modeling. Thanks for watching and see you later.